So, in a first problem, we have a disk of 40 centimeter in diameter and 5 centimeters thick is cast of pure aluminum in an open mold casting operation. Aluminum melts at 660 degrees, but the pouring temperature will be 800 degrees. The amount of aluminum heated will be 5% more than what is needed to fill the mold cavity. Why we always put more? Due to to take into account shrinkage effect. Okay, so in order to have the final desired dimensions, we always supply additional molten metal. So here they gave you the percentage. So we are heating 5% more than what is needed to fill the mold cavity. Compute the amount of heat that must be added to the metal to heat it to the pouring temperature, starting from a room temperature of 25 degrees. The heat of fusion of aluminum is 389.3 joule per gram. The density of aluminum is given to be 2.7 gram per centimeter cube, and the specific heat of aluminum is 0.88 joule per gram per degree. So here, first we are, if you want, in a problem of heat transfer calculation. So here we have an open mold. Okay, you know that for the open mold, it is the easiest type of mold. We don't need to have a cup and drag. We don't need to open the mold. So it is in general used for simple geometries. So here our purpose is to design a disk. So the geometry here is simple. This is why we can just use an open mold. So our purpose is to come up with a certain disk of 40 centimeter in diameter, and the thickness is provided. So this is the final product that we want to form. Okay, this is our final product. We have its dimensions. The final dimensions desired are 40 centimeter diameter. So here we have D equals to 40 and a thickness of 5 centimeters. So here we have T equals to 5. And first, this is the final product design. Okay, so here, from here, what can we calculate? We can calculate, if you want, the mass present here. Okay, now they said that the amount of aluminum heated will be 5% more than what is needed to fill the mold cavity. So here we can calculate the volume of the final product, but actually the volume that will be provided to the molten cavity is higher. It's 5% more. So if you want, the open mold will be of this shape. Okay. But we will supply a larger volume in order to account for shrinkage. Okay. So we can say that the volume, the molten volume, okay, will be equal to the final volume of the final cast, V final, V cast if you want, times what? Because they said the amount of aluminum heated will be 5% more than needed to fill the mold cavity, then we should multiply the final cast volume by 1.05. Okay, this will allow you to find what is the volume to be molten in this case. So we have that the volume of the cast, since it's a thin cylinder, okay, we can calculate its volume by pi d square over 4 times the thickness times t. Okay, this will allow us to calculate the final volume, and since we are supplying more, 5% more, so we should multiply by 1.05. This will give us, okay, what is the volume to needed to fill the mold cavity. Okay, once we have the volume, then we will use the density of aluminum given. So the density given will give us the mass to mold. Okay, so M is equal to rho times V, V that will fill the cavity, the Molten method. Okay, so now we have calculated what is the mass of aluminum to melt. Okay, and the second information we need to calculate the total heat that should be provided is to know the initial and final temperature to reach. So they gave us that the initial temperature is 25 degrees. So here in melting process, process, we have several steps. Okay, first we should increase the temperature from 25 to the melting temperature. So as a first step, I should increase the temperature from 25 to 660. Once I reach the melting temperature, I will have change of phase from a solid to liquid. So in this phase, heat will be supplied to aluminum in which form? Look, you have two forms of heating. You have sensible heating and you have latent heating. Okay? What is sensible heating? When we talk about sensible heating, for sensible heating, no change in phase. Okay? No change in phase. And this means that the temperature, so T will increase. Okay? So the first step in my heating process, okay, so phase one is a sensible heating phase, because in phase one, okay, I have T initial equal to 25 degrees, okay, and I am in which state? So phase one is in one state, is in solid state. So it's when I supply heat to my system, it will be a sensible heat phase, because my temperature should increase from Ti to what? So T will increase to the final temperature of phase one is T melting, okay, which will correspond to the melting temperature of aluminum. Here it is equal to 660 degrees. So as you can see here, I have a phase of, once I reach T melting, I will have change of phase. So in phase two, in my calculation, phase two will be we will have mixture of phases. We have in phase two, we have mixture of phases. So heat absorbed will not be transformed into increase of temperature, but will be used to change phase from solid to liquid. So in phase two, we have a mixture of solid and liquid states. Okay, so in this case, heat is transferred in the form of latent heat. This heat is transferred in form of latent heat in order to transform so I want to transform to from 100% liquid to 100% from 100% solid to 100% liquid. So let me here, maybe you cannot see it here. So what will happen in the first phase, I will have temperature increase, okay? In the second phase, I will have constant temperature. And then once I reach the 100% liquid state, I will start to have re-increase in temperature, okay? So first I have increase from 25 degrees to 660. This phase is a sensible heating phase. Then what will happen here, I will go from this point, which is 100% solid to 100% liquid, and this change of phase will take place at constant temperature. So So here it's 100% liquid. And finally, once I reach the 100% liquid state, now when I continue to supply heat, my temperature will continue to increase until reaching the desired pouring temperature. So here the pouring temperature is 800. So I will heat until pouring temperature, which is 800 degrees. So I can say that my heating will be divided into 3 steps. I will have here, this is called solid heating. So I have first solid heating, and of course it's a sensible heating. Then I have the change of phase. In phase 2, I have change of phase. So I have latent heating in this phase. And finally, when I reach 100% liquid and I continue to heat, this is called liquid heating. Okay. Now, concerning the total amount of heat, all I have to do is to add these 3 amount of heat. So I should calculate sensible heating during the solid phase. I should calculate latent heat during the change of phase. Plus, I should add to them liquid heating, which is a sensible heat. So now, sometimes if you want, I can calculate heating for these both stages, solid heating and liquid heating, in one step. And you will see why, okay? Because to calculate solid heating, what is the formula? Which formula I will use? How you calculate solid heating? It's a sensible heat. In heat transfer, how you calculate a sensible heat transfer? What do you need to know? What is the formula? Who remembers? Q sensible is equal to mass M times Cp, specific heat, times delta T. Okay, so here the mass is already calculated. I replace it. The specific heat is given to be, pay attention for your units. In specific heat, the unit is 0.88 joule per gram degrees. So in order to find in total, Q will be in joule. Okay, so in order to have Q in joule, M should be in gram, because C is defined per gram degrees. So M should be in gram. Delta T should be in degrees. Since Cp is provided in joule per gram per degree. Okay, in this way, when you multiply, you will get the sensible heat in joule. So here in the first phase, in solid heating, delta T is equal to 660 minus 25. So I get that this is equal to M, which is calculated, times Cp, which is 0.88, times delta T, which is 660 minus 25. Okay, so this is the sensible solid heating. Now, if I calculate the sensible liquid heating, so what will be? So as we have seen, Q solid heating is equal to 0.88 times Cp times 660 minus 25. Okay, now if I calculate the sensible heat of cooling, so Q liquid, if you want liquid heating, it's equal to the mass. Sorry, here it's C is 0.88, so here this is M. Okay? This is M, because C is 0.88. So for liquid heating, it is 0.88, because they gave us, we assumed constant specific heat here, because they gave us one value. Sometimes the specific heat in general vary with temperature. But since in the problem they gave constant specific heat, we will consider it as a constant. So it's 0.88 times m times the final pouring temperature, which is 800 minus 660. So if you want here, you can do the total sensible heating in one step, because as you can see, 660 will simplify. And هون it's plus, هون it's minus. So Q sensible total, because you have constant specific heat, we assume constant specific heat. Q sensible total will be equal to 0.88 times the final temperature, which is 800, minus the initial temperature, which is 25, times the mass, of course, times. Okay, so this is how we calculate the sensible heat. Now we should add to it the latent heat, and Q latent, also from thermo, is equal to the mass times what we call the heat of fusion. Okay, LF. LF is called heat of fusion. This is the heat required to change phase from solid to liquid. Okay.
دكتور
Yes.
أنا industrial engineering ما بناخد thermo مفروض نعرف formula صغار هيدول.
No. You are just responsible of what we solved together. Is it clear for you now, or you want me to repeat? I can repeat if it's not clear.
لا it's fine إنه هي it's just a formula ف
Yes,
what we
exactly.
have, I think,
Yes, you are just responsible of these formulas. Okay. Here the idea is that when you have one phase, no mixture of phases. When you heat, the temperature increase. Okay, and Q, the heat provided, will be given by mass times the specific heat C times delta T. While when you have a change of phase, the formula is given by mass times heat of fusion, because T is constant, so T will not change during change of phase. But what will happen? The state of your material will change from solid state to liquid state, and you know that in order to go from solid to liquid, you want to heat, because you want to provide extra energy. Why? Because in case of solid, the molecules are very close to each other, attached to other by strong bonds. So in order to rupture these bonds and have more freedom of motion of your molecules, you want to give enough energy that allows these particles to have rupture of bonds between them and to reach the liquid state. Okay, this is why you need to heat to go from solid to liquid, because you need to provide energy to molecules to get them from the solid state to liquid state. So in this case, this is provided by what is called heat of fusion. The heat of fusion is given in joule per gram. So the mass is here, the mass will be in gram, and the heat of fusion is provided in joule per gram. Now, in case you have the heat of fusion provided in joule per kilogram, then you replace M by kilogram, and you will have in total your latent heat in joule. Okay, so here, after calculating in detail the value of latent heat and the value of sensible heat, in order to find the total heat that should be provided, all you have to do is to do the summation, and that's it. Okay, you get then your final result. So to summarize, here you have the complete method. So first we calculate the volume, and since we have to add a certain percentage for shrinkage effect, we multiply by 1 plus 5%. Then the total heat required is divided into three phases. The first, this is the solid heating, this is the change of phase heating, and this is the liquid heating. So as we have seen together, okay, you can take into factor the mass, which is rho times V, because M is common to the three factors. Then for the first one, it's C delta T1. For the second one, it's the latent heat of fusion. And for the third one, it's M factor C delta T2, which is the pouring temperature minus the melting temperature. And as you can see here, you will obtain a value in joule, but in order, because it's times 10 to the power 6, you can convert it to megajoule. So you need 19 megajoule, which is a very large amount of heat, in order to change from 25 degrees to 800 degrees your system. Okay, and for example, here we can see that, for example, if you want to use a combustion, a certain combustion product, for example, here, if we take a combustion product giving 33 megajoule per liter, so we need with an efficiency of 60%, so we need here one complete, 1 liter of gasoline in order to provide this quantity, which is really a large amount. Okay, so we should burn 1 liter of gasoline considering an efficiency of 60%. When we talk about efficiency, you know that any combustion will have losses. Okay, so the efficiency is the useful, if you want, amount. So when they gave us an efficiency is equal to useful heat amount, Q useful, over Q total. Okay, so here, for example, what is the useful power I should supply? What is the useful heat? The useful heat is 19 megajoule. So since I know what is the value of useful heat, and I know that my efficiency is 60%, okay, 0.6, so I should provide in total 33 megajoule. And this 33 megajoule is produced by 1 liter of gasoline. Okay. Any question on this problem? So Anna, just Annabelle, as we said, okay, you are just responsible of these formulas. You know them. No, they are not in the slides, but I gave you them.
Yes, أنا هيدي سألتها قبل ما أرجع أسألك.
Okay, it's fine. Any other question? Anyway, I will give you a summary sheet. It's already present in the summary sheet I provided you, I said, because it was for several chapters. So you can find formulas of these in the formula sheet provided. Okay, yeah, guys. See you next time. Maybe next time I will post recording PowerPoint and we continue problems on Friday. Okay. Yeah. Let's see you. Bye bye.
Thank you, doctor.
Welcome. Bye.